Can you folks in the chat hear me? All right, folks, let's get started. So, as always, remember the seating survey. Section 002 is today's, so make sure you get that done. Upcoming deadlines. Today at 5 p.m., the first group activity is due. There have been some technical questions about how to do aspects of this. What you do when you come into the document, you go to File, make a copy of it, and then that creates a copy of it in your Google Drive. Since it's then your copy, you're able to modify the permissions. And if you click up here where it says Share, then a box will come up like this down here. At the bottom it says Get Link. If you click in that area, it expands, and you can then modify what it means for somebody who has a link. Either they can be a viewer of it, they can be a commenter on it, or they can be an editor of it. You will want for your entire group to be able to be editors. And then you hit the share button at the bottom, and then you click on the copy link portion, link up above, and you can then send that link to your group members so that everybody then can simultaneously work on the document. When you are submitting it to me, what you need to do is do the same thing. Make sure that it's in editor mode, or at least commenter mode. You then copy the link, and then on the submission page here, you have Submit Assignment link here. You click on that, and a dialog box opens up, which has an editor in it. Obviously, this is really hard to see on here. You paste the link into to that shared Google document into that editor window. Select the whole thing, and then click on the link that is Insert or Edit Link. And so then you are able to paste that link again here, turning it into a hyperlink rather than just a non-linked URL, and then select it to open in a new window and insert. Once you do that, it will give me a link I can click on to pull up your completed document. Okay. I know some of you have already done some submissions and have done it by other methods, such as creating a PDF of it and then sending me the PDF file, those sorts of things. This time around, that's fine. I'll figure it out as long as I get it somehow. But in the future, I'd like you to go through this process to kind of save on disk space. At 5 p.m. today, the submission of the group activities closes, and that's a hard deadline because at 5 p.m. the individual quizzes will open up for you, which you will then have 24 hours to do. So that is how most of the grading of the group activity is going to happen. You've done the group activity, you have your answers that you have come up with as a group, and then individually you then answer questions, almost all of which are directly from the quiz, from the document itself. And then that will end up getting graded. Words are failing me, sorry. You will be doing that part of it individually. For the group submission, for the group document, only one of you has to submit it, and it's marked as a valid submission for the whole group. On that quiz, there will be one question that asks you to extend your knowledge a little bit. It'll be, okay, take what you've learned from the activity. Can you then apply that to a novel situation, a new situation? And then at the very end, there's a free response section that's not graded, where you can describe anything to me that you think I need to know about the process of doing the group work. This is especially there for cases where, you know, one or two people in the group seem to be doing all of the work and the other people aren't. You know, I need to know about that and try to work on group dynamics to try to fix that problem. Okay. Once this is submitted, start coordinating with your group about the next group activity you're going to be doing, which I believe is going to be due next week. They are not going to be every week, but I think we do have one next week. I will get those files up onto Blackboard this afternoon. This next one is a particularly fun one. In my intro video, I mentioned that we're going to be demonstrating that an entire $15 billion per year industry is a fraud. That's the one we're doing right now, the next one. Okay, other upcoming deadlines tomorrow, Wednesday, the content video quizzes are due and the individual group activity quizzes are going to be due as well. And then Friday is homework 3. Okay, any logistical questions on anything before we start to get into some muddiest points? Okay, so there were a couple of muddiest point logistical things. I already talked about how to submit the group activity. What do I do when I haven't been able to reach my group? So I put a Piazza note up this morning that, so that if you are in that situation, you really have two options. One of them is to decide, okay, for this one, I'm just going to do it myself. And you can do that and just mark in the quiz that you do that that's what you did, so that I can take that into account when the grading's happening. And if that ends up happening, I will then be doing some shuffling of groups to get the people that are actually working out of groups where there are people that aren't working or not even communicating. The second option you have, if you don't feel up to doing this first group activity on your own, is to post a follow-up thread to my post that, where I'm talking about this and solicit other people who are in the same boat. So if there are 3 or 4 people, each from different groups, and they're the only ones that have been reaching out and haven't heard anything back from each other, you can form an impromptu group of yourselves. And that's perfectly fine with me. If you do that, then part of that follow-up thread, make sure you say, okay, we are doing this. And then I can come in as quickly as possible and reassign the group membership so that you have an easier chance of working together on it. I will be monitoring that thread all day. Okay. Then there was a further question, how are exams going to be formatted and administered? I am working on that. I had hoped to have that answered as of the end of last week. I'm starting to get some ideas of how I'm going to be doing it. It is probably going to be either a Blackboard test or a Knewton test, though it's not going to be the Knewton Alta adaptive learning kind of things. It'll all be custom questions that I'm putting together. I am anticipating being able to write it in a way where it is open resources, so you can use your notes, you can use the textbook. You can probably even use Google, because I'm going to be writing these questions in a way where it's not possible to just Google the answer. So I think that that is probably going to be the case with that. I'm considering giving you a range of days over which you can do it. So maybe have it open for about 3 days for you to do it. And I want to as well set it with a long enough time that it's available for you to do it that you feel like you have a chance to actually answer all the questions while thinking about it and trying to figure some things out. So I don't want you to have time pressure on you, significant time pressure on you. But given that I have not fully written the test yet, those are my anticipated guidelines, not necessarily a hard and fast rule about what my guidelines are going to be. Okay, so let's get into some of the content stuff. And we have quite a few of them today, which is good. That means there's a lot to talk about. Yes? If I will do a review session before the test, I certainly would anticipate that most of the sort of muddiest point days that are coming before the test would be devoted to things like test prep rather than really new material. Given that I don't know what my questions are going to be looking like yet, I don't know how easy it's going to be. I mean, what I would love to be able to do is to construct a test that is similar to the one I'm going to be giving everybody, but with tweaks so that these aren't exactly the same questions, but it'll give you a flavor of them, and have that as a practice test that people could have. Just timing is going to be the issue here as to whether I'm able to do that. A topics list? Okay. So, right. So in terms of a topics list, I think you should be able to look at the content videos and identify 3 or 4 topics per video that seem to be the main points. And that's generally what I would do. So intermolecular forces, you need to know what are the various intermolecular forces. And how do you tell whether a molecule has them or not? What properties of a molecule will make them stronger, or a particular intermolecular force stronger or weaker? What kind of effect do intermolecular forces have on properties like boiling point, melting point, surface tension, viscosity, things like that? So the topic list, if you've been paying attention to the videos, should not be very surprising because there are big picture topics that are, and many of the videos are titled with those topics. So one thing that I would actually recommend, and this would be a really good thing to do, would be to use Knewton as a way to, as a community, generate a study guide. And so you can go in to have somebody post a question about what are the main topics that would be associated with the intermolecular forces video. And people can go in and add them and edit them, and I can come in and make suggestions about things that might have been missed and so on. And you can, as a community, construct that study guide and make sure that you hit the topics. And if anybody starts a thread like that, it's labeled study guide for topic X, I'll definitely make sure that I keep an eye on that one. And if something's getting on that list that is really not something you need to be wasting your time on, I'll comment and mention that. Or if there's something that gets on that list that's missing from the list, that's a key concept, I'll bring it up. So I strongly recommend using that kind of, that resource for that purpose. Okay, let's jump into some of the topics. So we had a couple that are in the category of phases and phase changes. One person asked, how does a gas liquefy once it has reached critical pressure? So the idea here is that you have a gas that is at a high enough temperature that drawing the line across from that temperature point would horizontally take you above the critical point. So the molecules clearly have enough kinetic energy to escape each other, to escape their neighboring atoms, neighboring molecules. When you start increasing the pressure, essentially what you are doing is forcing the molecules that are bouncing around in the gas phase to be closer and closer to each other. So, as you are doing that, you are decreasing the space between the molecules. At some point, you will have decreased that space so much that the molecules are effectively in contact with each other all the time. You have squeezed out all of the excess space. At that point, the geometrical relationships between the molecules is going to be nearly identical to that of a liquid. So it didn't really liquefy in the sense that something caused it to coalesce. It's rather that you forced the molecules together so closely that they are still that they are the same distance apart that they would be in a liquid. So that is what's going on in the supercritical regime. Okay, and that's really that's the only way to liquefy it once you're above the critical pressure. What is a supercritical fluid? Well, that's exactly what I just described. It is a system where the molecules have enough energy to escape their neighbors, intermolecular attractions, but they don't have the space to take advantage of that. So they are extremely mobile, so they still definitely act as a fluid, but the molecules are in direct contact with each other throughout the substance because of the extreme external pressure. Okay, the next one we have is what is the difference between the triple point and the critical point? What do they indicate regarding the sample? Okay, so for a phase diagram, we have temperature on this axis, pressure on this axis. We typically have something that looks like this. So solid, liquid, gas. This is the triple point because it is the only place on the phase diagram where all three phases are present in equilibrium with each other. Okay. At a point on this line, only solid and gas are in equilibrium. On a point on this line, only liquid and gas are in equilibrium. Along this line, only solid and liquid are in equilibrium. This one point is the place where all three are in equilibrium with each other. Okay. This point here is the critical point. And that is the point above which the transition between liquid and gas stops acting like a phase change. And so beyond that point, you are dealing with something called the supercritical fluid. Okay, any clarifying questions on any of these phases and phase changes? Questions? Okay. Properties of solids. Okay. Since crystalline solids have more orderly arrangements, does that mean they have higher boiling points than amorphous solids? Well, the first question with this is boiling is the transition from liquid to gas, so there's a crystalline solid is not a solid by the time that you're at a boiling point. So maybe this means melting point rather than boiling point. And there are plenty of examples of crystalline solids with very high melting points, but there are also examples of crystalline solids with very low melting points. Can someone give me an example of each? What is a crystalline solid that has a very low melting point? So, okay, water. I would call water sort of an intermediate one. It's certainly not super high, but there are a lot of things that are much, much lower than water. So think of something that is normally a gas at room temperature.
Maybe iodine.
Methane. Iodine is actually a solid at room temperature. But methane, certainly. So other things that what's in our atmosphere? Nitrogen gas, right. The boiling point of liquid nitrogen is 77 Kelvin. Or negative, no, not, negative 77 C. It's one of those two. I don't remember which two that is, okay. Anyway, but it's pretty low. And so the melting point would be even lower than that. The reason that is such a low, has such a low melting point is because the intermolecular forces between adjacent nitrogen molecules or methane molecules are very small, essentially just dispersion forces. And there aren't a lot of electrons. There are some, but there aren't very many. So the London dispersion forces are not extremely strong in those cases. So that is a molecular solid with very low melting point, but it's crystalline. What is a crystalline substance that has a very high melting point? Diamond, excellent choice. It's a network solid. In order to melt it, you have to break covalent bonds. So I think somebody looked that up on Thursday and came up with something around 3,000 degrees as the melting point for diamond. So clearly crystalline substances can have melting points that range from ridiculously low to ridiculously high. Amorphous solids are similar. If you have a plastic, almost any plastic that you have here is going to be an amorphous solid because they consist of very long chains of molecules. You can think of them as like wet spaghetti noodles, and you throw that into a bowl, and then you make sure you don't have enough kinetic energy that the noodles are jumping around anywhere. So it's basically a solid at that point. But there's no long-range order going on because it's a disordered, tangled arrangement of all of the spaghetti noodles. Well, we have some plastics that are solid up through many hundreds of degrees. And there are some plastics or rubbers, think of like rubber cement, that are that have much lower melting points. So simply being amorphous versus crystalline does not tell you anything important about boiling points. Okay, how does an amorphous solid form? So I kind of went over that with the example of the spaghetti noodles. So it typically happens in cases where the molecules are large enough that they tend to be randomly configured. They're flexible enough that they can be randomly configured within the body of the substance. And so you tend to, as a result of that, to get an amorphous substance. Okay, so there are apparently some Knewton questions. Which of the following is a type of crystalline solid? And the student was wanting to know, how do I start answering that question? One problem is I don't know what the choices were on this kind of question. Do any of you have an example of that in mind? about what kinds of choices are available for that question? Okay, so if somebody comes up with one, we can come back to that. Just raise your hand and let me know. Otherwise, I will inquire about that on Knewton to try to find out more about what the question is. All right. Graphite has layers and so can transfer to paper. Is this the same for lead? Not really. The lead is a soft metal. So the properties of solids video talked a bit about how ductile and malleable many metals are, meaning that you can form them by beating them with a hammer or drawing them into a wire, because the metal atoms can slide past each other upon the application of some force, and it'll still not be breaking bonds very much because it's essentially these metallic cores floating in an electron sea that's surrounding them. Well, the hardness of the metal, its resistance to that kind of deformation depends quite a bit on how many electrons each atom is contributing to that electron sea. And so the elements that contribute a lot of electrons tend to have a much more rigid structure than those that contribute very few electrons to the electron sea. And lead doesn't contribute all that many electrons, so it's a very soft metal. And so when you have a piece of lead and you are writing with it on a piece of paper, which normally we don't do because people are trying to avoid lead because of health hazards associated with it, but people used to. And what is happening at that point is that the metal is soft enough and ductile and malleable enough that it deforms at the surface until it deforms to the point that it can have pieces of it just break off and get smeared onto the surface. So it's a little bit of a different phenomenon from what's going on with graphite, even though the effect macroscopically kind of looks like the same. You rub it across the surface and you leave a trail behind. Okay. A bunch of questions on unit cells and lattice types. So, the most popular one was a very specific question from Knewton. The edge length for the unit cell of nickel is 0.3542 nanometers. We were given a density, and we are asked, does nickel crystallize in a simple cubic structure? So, and then the general question that's resulting from this is, how do you use the density to find if something crystallizes? Oops. How do you use the density to find if something crystallizes? So a clarification to that question. This question is not asking, does it crystallize? It's asking, when it crystallizes, is its structure simple cubic? Okay, so the density is not going to tell you does it crystallize or not. So what we're really getting at is simple cubic. Now, and we're supposed to be doing it using a density. So what is density? Mass per unit volume. So density, usually given the Greek letter rho, is mass over volume. Okay, now if I take, so this is nickel. If I take a block of pure nickel and calculate its density, and then I take a microscopic grain of nickel and calculate its density, are those going to be the same or different? Yes. Maybe different? Why would they be, which do you think would be more dense? When it comes to what?
When it comes to, yeah, exactly. When it comes to what was the comparison again?
So we have a block, a macroscopic block of nickel, and we have a microscopic grain of nickel. Are those two going to have the same density?
Well, because there would be more mass cube than there would be in the grain of nickel.
Okay, so there's going to be more mass in the block than in the gram. But what about the volume? There's going to be more volume in the block than in the grain as well. And so if you double the volume, you're also doubling the mass. So will the densities be the same? Yes. So density, so what that means is we can pick whatever size of sample we want in order to calculate the density. The simplest, the smallest block we can pick is going to be a unit cell. So that's what we're going to do. So in a simple cubic unit cell, and so it is always good to call up a picture when you are when you're trying to solve one of these problems, so that you have in mind what the unit cell looks like. Okay? And if you're doing this on a homework, if you're doing this even on the test, you can call up a picture from somewhere rather than having to remember and draw it from scratch. So we have here a unit cell. How many atoms do we have in the unit cell? Okay, I see somebody holding up a single finger. 1, that's right. Because we have 8 corners of atoms, and each corner is 1/8 of an atom, so it has a grand total of 1 atom per unit cell. Okay? We have found previously the packing density for a simple cubic unit cell. We've gone through that calculation in class here a couple of times, and there's at least one Piazza question where I go through it in detail with pictures. And we came up with it being 52% of the space is is made up of the, what am I trying to say? 52% of the space is made up of the atom, and 52% is the empty space. Okay? We also know that our edge length is going to be, we're told in the problem, 0.3524 nanometers. Okay? So we now try to figure out how to take all this information and figure out a density. So we can find the volume, remember our density is mass over volume. So we have a side length of the cube. We cube it in order to get our volume. And we have 1 atom of nickel, giving us our mass up top. Well, we know we have 6.022 times 10 to the 23rd atoms of nickel for 1 mole of nickel, right? and then multiplying, how do we get from moles to a mass? We use the molar mass. So we're going to have 1 mole of nickel in the denominator so that the moles cancel. Does somebody have a way to look up the atomic mass of nickel? $58.69. Okay. So let's look at things canceling. We have atoms of nickel, moles of nickel, moles of nickel. So now we need to get this nanometer cubed that we're going to have here into something that is better for us. And we notice that the density we're working with here is in cubic centimeters rather than cubic nanometers. So if we think about nanometers, that's going to be 10 to the 9th of them in a meter. That's what nano means. So we can write 10 to the 9th nanometers. And that's going to be equal to 1 meter. But 1 meter is also 100 centimeters. So we can put 100 centimeters here. Now that's going to cancel one of these 3 nanometers here. So we need to cube this to cancel all of them. Then the nanometers are going to cancel, and you will end up with grams of nickel over centimeters cubed. And then we just have to plug in the numbers and do the math to find out what the density is that you get here. So this cubed in the denominator, we're dividing by Avogadro's number, we're multiplying by the molar mass of nickel, and then we've got this unit conversion factor cubed, which is going to end up being, it's going to be 10 to the 7th, so you're going to end up with 10 to the 21st in here, and you'll come up with a number. Then all you do is then you say, okay, I have that number I just calculated, assuming it's simple cubic. I have this experimental density. Are they the same? If they are, then nickel does indeed crystallize in a simple cubic structure. If it does not equal that, then it's clearly a different structure. Does that process make some sense? Okay. All right. How do you find atomic radius given unit cell edge length? Okay. You're kind of doing a greatest hits thing here, which is fine. So, as always, start by drawing out or calling up a picture of the unit cell in question. Okay. So, if we are doing simple cubic, this is what we have. Excuse me, that should be actually meeting there. And what we see is that the points of contact between the adjacent spheres lies directly along an edge. That means that this is a radius of the atom, and this is a radius of the atom. So the edge length equals 2r. What about face-centered cubic? Okay, we know that we're going to have a sphere here. That should probably be bigger, shouldn't it? Yeah. We've got corners here, like so, and the points of contact are going along the diagonal here. You've got a point of contact here and a point of contact here. So what we have here is that this is R, this is 2R, this is R, so the face diagonal equals 4R. Now, but we need to get to edge length, since that's what the question's asking about. So we'll call that E. So this is an edge length, this is an edge length. It's a right triangle, so we can use Pythagorean theorem to find the relationship. So E squared plus E squared equals 4R squared. Okay. So 2E squared equals 16R squared. E squared equals 8R squared. And E equals 2 square root of 2R. Okay? So it's just geometry. Body-centered cubic. Okay, so we have our corners. And we have in the middle some kind of sphere in the middle. My diagram is not very good, but what hopefully will be clear is that the points of contact between the spheres are going across the body diagonal. So from this corner of the cube to the back corner of the cube here. So we have 1R going from the center of the sphere to the edge of the sphere. We have 2R as the diameter of the central sphere, and then we have one more R to get us across the radius of the sphere that's at the corner. So there we have the body diagonal is 4R. And at that point, you then use trigonometry again. So we could draw this line, which is a face diagonal on the bottom. And so we have E here. And this one we already determined is 2 square root of 2, no, that's 2 square root of 2R. But that's a different system. So, so we can find this one if we have, okay, green triangle. E, E, we'll call that F for the face diagonal. So 2E squared equals F squared. And so F equals square root of 2E. All right. This triangle, which is also a right triangle, we have E squared plus F squared equals, our body diagonal, we'll call it B, B squared. Well, we know what F is from this. So E squared plus 2E squared equals, and we know what this is in terms of R. This is going to be 4R squared, quantity squared. So 3E squared equals 16R squared. We divide through, so E equals 4 over square root of 3R. So all you are doing to make the connection between edge length on the unit cell and the radius of an atom is visualizing the arrangement of the atoms in the unit cell, identifying where the spheres are touching, because that's how you identify where radiuses are. Identify where the spheres are touching, and then use simple geometry to get between the two. Okay. All right, any clarifying questions on that? Okay. How do we determine coordination number from a known unit cell lattice type? Okay, I have printed up some visual aids for this. So let us start with simple cubic. Okay. As always, you need to have a visual representation of the unit cell and sometimes of neighboring unit cells as well in order to answer questions about the unit cell. So simple cubic is just one of these cubes that you have. So this here would be a unit cell. But all of the atoms are on the corners, meaning that this atom here is in 8 different unit cells. 4 that are close to us, 4 that are further away. So in order to look for nearest neighbors, that's what we have to do. You have to look at all of the potential nearest neighbors that we could have. So clearly, going along this edge takes us to a nearest neighbor. That 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 one does, and that one does, giving us 6. Now, what about some other possibilities? What about going to here? How do we know that's not a nearest neighbor? Yes?
We know that only adjacent corners for the simple cubic, like it only touches on this.
That's right. They only touch across the edges. And we can, and because these are squares, these faces are squares, we can, this distance to here is going to be the same distance as this distance to here, right? So that compared to this, that's the hypotenuse of a right triangle. And so that has to be longer than the sides are. So we have correctly counted up all 6 nearest neighbors for this. All right, let's look now at body-centered cubic. Okay, so we get a good picture of it, and these are useful for different things. This one actually shows us where things touch, but in 3D that's kind of hard to see. This one abstracts it a bit more and shows us where the centers are. For this atom, it should be pretty clear that all 8 of the corners are equidistant. So it has a nearest neighbor distance of at least these 8. But you could imagine that maybe something that's in the next neighboring unit cell might also need to be counted. So let's draw one more unit cell up here. And there's another one right here, right? So these are clearly too far away. What about this one? Is this one the same distance away as these? No, it's not. So this right here is the same distance as the unit cell length side here, right? This distance and that distance, those distances there are smaller than this because this is a right angle. And so we have a triangle where the hypotenuse has to be longer than those. So in the body-centered cubic structure, the number of nearest neighbors, and therefore the coordination number for the central atom is 8, because there are the 8 corners of its unit cell. But what if instead we decided to look at a corner atom rather than the center atom? Now in the video, the content video, I took you through visualizing how just by changing how you're looking at this. So if you imagine the lines going away but the atoms staying in place and extending this in all directions like this, and then another one back, then you can start to draw a different unit cell that's going that way, which has in its center another atom that used to be a corner. And you end up with a structure that is also a body-centered cubic structure. It's just you've swapped the corners and the inner spheres and the inner atoms. So this picture down here illustrates that. So it's showing that for a central atom, the nearest neighbors are the 4 corners on its unit cell. If you're looking at a corner atom, its 8 nearest neighbors are the body centers in all 8 of the adjacent unit cells. That makes some sense? Okay, so that's how you find the coordination number for body-centered cubic. Now everybody's least favorite, face-centered cubic. Okay, this one is a little harder to visualize. You can see, hopefully, if we pick a face atom, that, and that are all equidistant and are very close to each other. It turns out, though, that that distance, that distance, that distance, and that distance are also that same distance away. And we can prove that with geometry if we need to. And then since this is half in this unit cell and half in the next unit cell, there are going to be analogs to those 4 that are pointing out the other way for a total of 12 nearest neighbors. It's kind of visualized here where you have this is the central atom and you can see where all of those nearest neighbors are. But you may also remember that we had an alternate way to construct a face-centered cubic, which we called cubic close packing, where we are laying down layers of atoms. This is kind of taking the cubic structure and putting it up on a point and then looking at the layers horizontally once you've done that. And if we look at it this way, remember that each atom that we pick, let's pick this as our central atom right here, we have put down into a nestling spot that's in between 3 atoms that are on the prior layer. So there are going to be 3 nearest neighbors that are on the underlying layer that are all touching that sphere. On its own layer, there are going to be 1, 2, 3, 4, 5, 6 atoms that are touching it, that surround it. And then the next layer that goes on top is going to be kind of an inverse of what's underneath it, where there are going to be 3 more atoms that are touching it from up above. Okay? So again, we have 3 plus 6 plus 3, which gives us 12 as the coordination number, the same number we got by analyzing it in these ways up here. Okay, so that is how we determine coordination number from a known unit cell or lattice type. It really does come down to looking at the geometry visually, maybe even building some models. I mean, get some marshmallows and toothpicks it can be, or gumdrops and toothpicks. It can be really powerful to be able to hold it in your hands and rotate things around. And you can even use different colored gumdrops to indicate I'm focusing on this, this one atom so that you can see things more clearly. Okay, from Newton. Which metal crystallizes in simple cubic structure? So the correct answer to that is polonium. It is the only one that does. How do you figure this out? Well, that's one of those kinds of questions I don't like asking, because the way you figure it out is that the chapter said it when it was listing it, listing the various things that form a simple cubic structure. They say there's only one element that, that packs in a simple cubic structure. It is polonium. And so this is kind of remembering the trivia detail that nobody cares about. So on an exam, I will not be asking you, do you remember the trivia detail? But additionally, Newton asking this question makes you as students feel like there should be some way to say platinum, I should be able to figure out which structure it is in. You don't have the information to do that. So I'm not going to be asking you to determine which crystal structure it is just by being given which element it is. Now, we saw an example earlier here for the nickel example, where you're given some data and you're asked, is it simple cubic? But that's taking the data and seeing, is the data consistent with simple cubic? That's not, you wouldn't be able to do this without that extra data. Okay. Finding face-centered cubic density given a unit cell length. So up here, we did something very similar to this for the nickel. So we took nickel with a unit cell length, we assumed simple cubic, and we found the density. And then we were comparing that density to this to see if the hypothesis that it is simple cubic is correct. The only difference here is you're doing it in face-centered cubic rather than simple cubic. And so in face-centered cubic, you have this structure. There are 4 atoms per unit cell. So when you're doing your density calculation, was here. So when you're doing the density calculation of mass over volume, instead of having 1 atom, you're going to have 4 atoms because there are 4 atoms in the unit cell in a face-centered cubic arrangement. And then the relationship between, and actually, yeah, so, and you don't even need to be worrying about the body center diagonal because you're given a unit cell length. You're given the unit cell size. So you just cube that to become your volume in the denominator. So, so this has no new concepts in it at all. You just, if you're finding a density, you know you need mass over volume. What is your mass? How many atoms are there? What is your volume? Well, you have an edge length, you cube it, since it's a cube. That's it. Is there a difference finding the radius of face-centered cubic and body-centered cubic? Yes, because the points of contact are different. So in face-centered cubic, the points of contact are along a face diagonal. In body-centered cubic, they are along a body diagonal. So that is the visualization difference you need as you start working the geometry. How did scientists discover cubic unit cells? So one of the biggest hints was finding macroscopic crystals that were cubes. And that suggested that whatever the underlying structure was, it was probably going to be cubic as well. More precisely, there are ways to use something called diffraction to make these determinations. So imagine an experimental setup here where you have a laser that shines out a beam of laser light, and it hits something with a single slit in it. The laser light goes through, and you have a piece of photographic paper here, and then take this up and turn it on its side, and what you see then is a band of the light that's coming through. And it's spread out because of some diffraction that happens along the edges. If you change this experiment now so that there are two slits, so there's a slit here, and now maybe there's a slit here as well, and the laser beam is passing through both of them, you don't just get two regions where the light hits. You get something that looks like this on the bottom, and hopefully you can see that there are a bunch of vertical lines going through here. This is called a diffraction pattern, and it is the behavior you see when waves interfere with each other. So if you take a perfectly still pool, and you have two big bobbers in it that are going up and down, creating circular waves. And the outgoing waves extend from each other until they run into each other. You're going to get this sort of cross-hatched pattern of regions of high wave intensity and regions where the surface is almost completely still due to what's known as constructive and destructive interference. That kind of behavior happens when you shine something through or bounce something off of a material that has a regular pattern in it. So think about something like driving past an orchard, and you see the rows of trees, and you see lots of different ways you could look at rows of trees as you're driving past and they're moving. That kind of regular arrangement can make very strong diffraction patterns. And so one can use X-rays, shoot them at a crystalline solid, which has a structure that looks like this, and get a very complicated pattern down here. That's where the physical principles of what's going on here are identical to the physical principles of what's going on making this interference pattern right here. And from this pattern, you can extract where everything is in the unit cell. It will tell you, it takes a while to do it. It takes quite some intense math to do it. But you can transform this information into a picture of where all of the atomic centers are in a unit cell, how much they're vibrating even, what are the edge lengths of the unit cell, things like that. So this is the best way to demonstrate what's going on at that sort of molecular level. Okay, part of that question was also, how is it that there's only 8 atoms that can fit in a simple cubic unit cell? Well, it's actually only 1 atom that fits in the simple cubic unit cell. It's 1/8 of an atom 8 times that can fit into it. But remember what the definition of a unit cell is. A unit cell is the smallest unit within a lattice that repeating it in multiple directions will regenerate the entire lattice. And so for simple cubic, there is only a unit cell that contains 1 atom, 8/8 of atoms, is the smallest unit that can be repeated in all those directions. That doesn't mean that you're ever going to have 1 unit cell and there are only 8 atoms in it. A unit cell is part of a larger lattice structure. It's a mental subdivision that we make to describe whatever that smallest unit is. Okay. Why do simple cubic structures exist? They seem pointless, particularly with their very low packing density. Well, the only simple cubic structure that exists is polonium, and why it exists in a simple cubic structure is a current research topic. There are One of the better papers I found was only published about 2 years ago looking into this, and you have to go really deep into quantum mechanics to understand why. So there is no good general chemistry level explanation for why polonium does this. And I'm not going to be asking you things like that. But the fact that it is the poorest of the regular packing arrangements in terms of packing efficiency is a good reason for it to be rare. But why does a particular one do that is way beyond what we can do in this class. I think we already handled finding atomic radius, unit cells, and differences between the two type. And I think we also calculated the density for unit cells and examples. Let me put that away. All right. Okay, some thermodynamics here. Okay, I'm going to do these first because they're quick, and I'm going to end on this one. How many moles of Si2N4 are in 3.4 liters of a 2 molar solution? So there are a number of questions similar to this that have come up on Piazza, and almost all of them are dimensional analysis questions. And that's really all you need to know in order to solve these problems. Noticing that there were that many questions on dimensional analysis problems, it made me feel as though this class's background in dimensional analysis may not be as strong as I had hoped. So I put together a video that I plan to use when I teach 111 on dimensional analysis, and I combined into it stoichiometry as well, but you can stop when you get to that point if you wish. It doesn't have embedded quizzes, it's just an extra video if you are having trouble with dimensional analysis. So what we are doing, dimensional analysis basically proceeds by 4 steps. Start with what you know. Multiply by 1. Repeat step 2. Arrive at the answer. Now, when I write it this way, steps 2 and 3 sound completely useless, and step 4 sounds like magic. But what I'm going to show you is that by careful, clever use of step 2, we can solve almost any chemistry problem by just applying these steps. And the key is understanding what we mean by 1. So we know that any fraction where you have the same thing in the numerator and in the denominator, that equals 1. Okay? The example I use in the video is alligator over alligator equals 1. And we also know that when you multiply something by 1, it doesn't change. So we can multiply something by 1 as much as we want, and it doesn't change. Now the trick here is, what do we do, why would we ever want to multiply by something in this kind of format? Well, let's suppose, one example you already know about is if you've got 3/4 and you're trying to add it to 1/8, you need to get common denominators. So you multiply by 2 over 2 to get 6/8, which is the same as 3/4, just written in a different way. Right? That's the kind of thing dimensional analysis does. But let's suppose that what we're looking at is 100 centimeters. Now let's use a molar mass for this. So 12 grams of carbon equals 1 mole of carbon, right? That's what the molar mass means. Well, if we take this and we divide both sides through by 1 mole of carbon, 1 mole of carbon, then this side cancels. And so this thing is just 1. So this whole thing where you're multiplying by the molar mass, 12 grams per mole, what you're doing is just multiplying by 1 in a way that lets you cancel units. That's all it is. So with that general idea, how many moles of something are in 3.5 liters of a 2 molar solution? Well, let's see. You start with what we know, 3.5 liters. And remember, what it's liters of is part of the unit. Okay? Now, we have a concentration. So concentration of 2 molar means 2 moles of Si2N4 in 1 liter Si2N4, right? So we are going to now use this as a conversion factor. 2 moles Si2N4 over 1 liter Si2N4. And I did that so that the liters Si2N4 cancel. We now have 3.5 times 2, or 7, moles Si2N4. So there's no formula you need to be memorizing for this. It's start with what you know, look at the conversion factors you have, and arrange them in ways where the units cancel to give you what you want. You're not applying a series of formulas, you're constructing a solution. Okay. How do we know when a substance is conducting electricity? So the way you would tell is if you have it hooked up to a power source, is there a current that flows? But I think what it's asking is how do you know if a substance that you have will be able to conduct electricity? And the answer to that is you need to have mobile charge carriers of some kind. So the mobile charge carriers could be, like in a solid metal, they could be the electron C itself. So electrons can get injected on one side and pulled out on the other side, and the electrons, because they're in this delocalized C, can just flow from one side to the other. They could be mobile ions. So if you have a block of sodium chloride salt, solid, it has ions, but they're not mobile, so that is a very good electrical insulator. But if you melt it and you put electrodes into it, it will conduct electricity very well because the ions are mobile. If you dissolve them into a solution, so making salt water, that will conduct electricity because the ions are mobile and they can act as the charge carriers, taking moving positive charges one way, negative charges the other for a current to flow. Okay. Whoever asked this question down here, I think I need a further clarification on it. So if somebody comes to that and wants to clarify it on Piazza, that would help. And I don't really have time, I'm up against the wall on time to be able to do this one right here. So I will make sure this one is the top of the list for tomorrow. Those of you that are not going to attend virtually tomorrow, it will be the first topic that's covered in the video that is going to be posted, so you'll have access to that. I'm finding that the videos become available to me sometime about mid-afternoon, and so usually before the end of the day, when the class has happened, I'm able to get the video along with its timestamp index up onto Blackboard for you. Okay. I have run us over time. I apologize for that. If anybody has any questions, come on up. Okay, sounds good.
So due date today is the
Thank you.
group activities and the video.
And the content video quizzes, yes.
Quizzes today or
Yes.
quizzes is Wednesday.